Well, I'll introduce our final speaker of this session. Susannah Dorfman from Michigan State University will be presenting how can synchrotron facilities support experimental petrology for the deep mantle and core.
Thanks, Claire. This has been great company, and I'm really enjoying everyone's talk so far today in this session, continuing after lunch. I have taken a little bit of a different style for my talk this afternoon. Instead of talking about a single project or a couple major projects that we've been working on in our group, I thought that I would focus instead on the Earth and Time report that has come up a few times. I had nothing to do with the writing of the Earth and Time report myself, but I have read some of the major bits of it. When it's been mentioned, we've also had some, I think, some complaints about whether the Earth and Time report really speaks to our high pressure earth science community, as part of the broader NSF-EAR community. But as preparation for our discussion that follows this talk and for the proposal that's coming up, I thought I would try to take ownership of this report, because I do think that there are several major areas of the report that are obvious for us to contribute to, and I've highlighted them here. The distribution and cycling of critical elements in the Earth was one. Critical elements means something very specific to some of our earth science communities, but if you look at how it was written in the report, the list of elements that they have there is exhaustive. Their definition of critical elements is closer to any element that you think of as important in the Earth. So this is absolutely something for us, whichever element cycle we're interested in. The origin of plate tectonics is something that involves whole planet dynamics, really, and is something where we have a reason to give constraints on what composition and what conditions have to say about this major problem in earth science. The generation of Earth's magnetic field, Bruce's talk this morning kicked us off talking about that a lot. That's an obvious one for us. And the generation of earthquakes and volcanism. While these are relatively shallow compared to Earth's magnetic field, I think many of us are concerned with the physics of why earthquakes stop happening with depth, what we know about shear and deformation conditions deep in the Earth, and what we know about the melting deep within the Earth that is the origin for volcanism at its source. So I also would highlight a few different physical properties and things that we need to measure that touch on these different areas. Partitioning and fractionation are key things for us to measure in order to understand the distribution and cycling of elements in the Earth. We need to be able to accurately determine, for example, we've mentioned earlier today, partitioning at Earth's core mantle boundary between silicates and metals. Redox and complex electronic behavior. We need to know the oxidation states. We've been talking about that for most of today, how we have different redox states possible for iron and for carbon and other elements that we have within the Earth, and how these redox states can be important tracers of the history of Earth's oxygen cycle, for example. Iron and other transition metals have complex electronic behavior that we've observed at very high pressure. Without our high pressure experiments, we have very little understanding of this. Melting and crystallization are big themes from our previous few talks, and throughout all of these different problems, if we don't understand the conditions of melting at the inner core boundary versus at the core mantle boundary versus as the magma ocean solidified, all of these are key problems for us. And we've also been talking about strength, plasticity, anisotropy. These also relate to places in the Earth where deformation is taking place, which is going to be involved in the generation of earthquakes and in plate tectonics in general as an expression of mantle convection. So One of the things that is also a clear theme, though, is that as we get to more and more extreme conditions within the Earth, it becomes more and more challenging for us to talk about the complexity of these different types of phenomena. When we are talking about lithologies, we're talking about multiple phases. Having multiple phases in the diamond anvil cell at a time reacting at equilibrium is still a challenge. We have to have controlled sample composition and geometry in order to do something that we could call experimental petrology in a diamond anvil cell. The reason why experimental petrology and experimental rocks physics communities don't tend to really think of themselves as high pressure people usually is because the high pressure community is cast more as a community of people that deal with single minerals at a time. When we are dealing with rocks, it often is important for us to use multiple complementary techniques. So we need in situ techniques in order to understand what's going on during the experiment. But often that's not enough for us to be able to accurately measure the chemical compositions. We also need ex situ techniques, such as electron microscopy, in order to more accurately determine with higher spatial precision what's been going on in our samples. And this is one of the things that we hope to be changing with some of the new synchrotron developments that we're talking about. One of the things that's also been challenging for us, in our ultra high pressure experiments with a laser heated diamond anvil cell, we have difficulty controlling the sample stress and temperature conditions relative to people who use larger volume presses. So all of these things are challenges that play out in this inverse relationship that we have here between the complexity in the experiment that we typically have and the maximum pressure. But in order for us to push the science forward, we really need to do both things. We need to be pushing for presses that can reach more and more extreme conditions, but we also need to be using the presses that we have to be doing more complex experiments so that we can really start to take over deep earth rock physics, a deep earth petrology. So what I'm going to do is I'm going to showcase a series of things that fit into these categories that relate to work that we've been doing in our group at Michigan State. Some of these are more or less of a stretch, but as a community, we definitely can own these scientific problems. So first, in terms of the origin of plate tectonics, I've shown here this cartoon that came out of my student Ming-Da Liu, who defended this spring. In his dissertation, he presented this cartoon to show our overall concept of the possibility that some subducting slabs go all the way down. Some subducting slabs may stagnate in Earth's transition zone. Whether this is something that's real or whether this is something that's an artifact of a moment in time captured by a seismology snapshot is an open question. But one of the things that's at the heart of whether this is feasible is the buoyancy of the lithologies that make up the slab. Ming-Da and also Jiaqiao Liu, who was a postdoc here a few years ago, have been continuing to work on really what Jiaqiao started. The original intent was to look at what happens to ferric iron in subducting slabs. What he was surprised to find in his experiments was a consistent and reproducible breakdown of his charges into two different phases. We were getting an iron-rich silicate phase as well as an iron-poor silicate phase. The iron-rich one being very ferric. This is about 50% Fe2O3. And the less iron-rich one being dominated by ferrous iron. So based on these experiments, this suggested to us that we could have a coexistence of a ferric iron-rich bridgemanite and a ferrous iron but iron-poor bridgemanite at certain conditions in the mantle. So we've been continuing to work out the physical properties and the phase equilibria in assemblages containing these materials. And the only way for us to take this on is to combine our in situ synchrotron techniques and our ex situ techniques in order to get a more reliable handle on the composition. What we're looking at is how these minor dense phases, such as a really iron-rich silicate here, would affect the buoyancy of a subducting phase assemblage, or the buoyancy of material that perhaps had segregated early in Earth's history at the base of the magma ocean. How is that going to behave as part of mantle convection? And how is iron going to be partitioned with other minerals? So again, when we looked at the distribution and cycling of critical elements in the Earth, iron was an element that they included in the list. And iron is absolutely a critical element for understanding the story of the Earth. It keeps coming up again and again, not just, of course, for understanding the core, but also for understanding the mantle. Nearly every phase that we have in a pyrrolite composition mantle takes up some amount of iron 2+ or iron 3+. And in this cartoon, we're highlighting in different colors of red, basically how much iron we expect to be in those different phases, where we're seeing the proportion of each of these minerals, pyroxene, majorite, perovskite, that is bridgmanite, and so on, as a function of mantle depth. So our basis for how much iron should be in these different phases is partitioning measurements. Here is one that we published just this year that was based on my postdoc work, actually back in the EPFL in Lausanne, where we were looking in iron-rich compositions at the partitioning of iron between bridgmanite and magnesiowestite in order to better understand superdense heterogeneities in Earth's mantle. So, we would not be able to do this experiment without the ex situ techniques combined with the in situ techniques. When we tried to use in situ techniques to measure the amount of iron in these phases, the error bars that we were dealing with are still on the level of 10% in terms of the iron content. So we're not able to, with great accuracy, use diffraction to measure the amount of iron in bridgmanite and in the oxide phase, compared to what we can do, of course, if we cut it open and take it to an electron microscope. Another critical element is oxygen. I haven't been studying oxygen directly, but this theme of ferrous iron versus ferric iron relates to the redox state of the Earth. And that tells us things about the cycling potentially of oxygen within the Earth. We heard earlier from Leonid of the potential, much greater complexity for oxygen cycling in the deep Earth, depending on how many of these complex oxide phases we consider to be potential phases in the Earth. And we can rightly point out that the redox state of the mantle is connected to the outgassing of the atmosphere. And therefore, the oxidation state of the Earth in Earth's mantle has set the composition of the planet. What we would also like to be able to do is determine whether we can measure using seismology what the oxidation state of the mantle is now. And so what we set out to try to determine was whether the seismic properties of oxidized bridgmanite and reduced bridgmanite as proxy for oxidized mantle and reduced mantle could be distinguishable. And we did by carefully controlling our sample composition, systematically working with ferrous compositions and ferric compositions, and also by working with very iron-rich compositions that helped us to make a tight constraint of the effect of iron on properties such as the bulk modulus. We determined that there is a difference between the effect of ferrous iron and ferric iron on bridgmanite. While we can see it quite clearly here at these high iron contents that we looked at, if we look back down to a more realistic mantle content of about 10% iron, the amount of difference that we would get in our incompressibility based on whether it's 2+ or 3+ ends up being quite small. So we're really on the edge of the possibility of being able to detect whether we're looking at ferrous iron or ferric iron. And what would be even more difficult would be detecting whether we're looking at high spin iron or low spin iron. We also needed to have a combination of different in situ synchrotron techniques to work with problems such as this. When you're interested in things like redox state and spin state, we of course need to be able to combine our techniques such as X-ray diffraction, sensitive to structure, sensitive to compressibility, with techniques that are directly sensitive to our valence and spin state of iron. So it was really important for us to be able to combine in this work. We had nuclear forward scattering, as well as X-ray emission spectroscopy to constrain the state of the iron. And the third critical element that I wanted to mention is carbon. We did some work in our group looking at the stability of carbonates in Earth's lower mantle in contact with iron. So first we were trying to understand the stability of carbonates in a reduced redox environment. And then we have followed up on that with our more recent work led by Ming-Da Liu again, where we looked at the carbonates in contact with silicates. And both of these studies suggested to us that at the base of the lower mantle, calcium carbonate is a potential host for oxidized carbon. So once again, in this image, you're seeing an element map from the ex situ microscopy. This is done in a transmission electron microscope. When we're mapping here, in white is carbon, red is iron, blue is calcium, and green is magnesium. And you can see that in addition to the calcium carbonate that's indicated here in blue, we can see these little white crystals, and these are diamond. We see carbon and none of these other elements present. So therefore, we're able to identify the diamond that's crystallized in this experiment as well. Okay, composition of planetary cores. Like others who came before, we are also interested in the potential minor elements that alloy with iron that could be important for powering the outer core dynamo and explaining the anisotropy of the inner core. My current graduate student, Allison Pease, is working on a project on deformation of iron nitride. As we've noted, a lot of us who are doing this type of work are working at room temperature primarily, which is not, of course, what the real Earth is operating at. But that's kind of a measure of the state of the field. We have to take this first step and first try to understand the strength and deformation properties at room temperature before we add the additional complexity of measuring these properties at high temperature as well. We know that this is going to have a substantial effect on both the elastic strength and the plastic deformation mechanisms when we apply temperature as well as non-hydrostatic stress. Ming-Da has done some work also on the iron nitrides, looking at the spin transition that we observe in nitrides. It's analogous to an electronic spin transition in carbides, sulfides, phosphides. All of these alloy systems undergo a subtle electronic spin transition, which has a subtle effect on the elasticity. That's important for us to be able to determine the composition of planetary cores. So by, again, combining a set of complementary synchrotron techniques, it was essential to have X-ray diffraction as well as X-ray emission spectroscopy in order to see where this spin transition is and to see that it has a second order effect on the equation of state. That was when we plotted it in this way by normalizing stress versus effective strain, we were able to see this change in slope at the completion of the spin transition that corresponded to that same pressure where we have become entirely low spin here. Jia Chao also did some work using the Paris-Edinburgh press at HPCAT, where our original intent was to look for the liquid structure of the iron alloy to better understand how the outer core liquid works. But we also discovered that above the liquidus, we were observing bubbles of nitrogen. We were observing an immiscible iron-rich liquid with a nitrogen-rich fluid in the iron nitrogen and iron nitrogen carbon systems. So by combining the in situ radiography, diffraction, as well as ex situ microscopy and spectroscopy to measure the composition of the alloy that's recovered, we were able to work out this phase diagram at pressures up to about 7 GPa and determine what possible impacts this would have on exsolution of nitrogen during impacts and accretion. And finally, a couple of notes on generation of earthquakes and volcanism. This is something, again, that's really hard for us to do with the diamond anvil cell. We have a very difficult time controlling stress in a systematic way. We can squeeze our diamond cell using a quasi-hydrostatic pressure medium, or we can squeeze it without a pressure medium to try to maximize a uniaxial non-hydrostatic stress. And the latter is what we've typically done when we're trying to get at shear properties and deformation. What I'm showing here on the right is an image of a model that attempted to determine the magnitudes of non-hydrostatic stress that are actually present in subducted slabs. And you're seeing here that these purple bars are on the order of 100 megapascals. So, this is at a level where we would like to be able to choose to select a 100 megapascal shear stress in the diamond cell. So I wanted to quickly highlight my student, Ben Brugman, who graduated this spring and was working out systematically the effect of different rare gas solid pressure media on the hydrostaticity of the chamber. So in particular, he was looking at krypton and xenon. Here in the right figure, we're showing differences in the ruby lines and comparing the difference that we see in krypton and xenon to the difference that we would see in helium and neon, which are more hydrostatic. And this figure on the left illustrates some work that we were doing trying to control the non-hydrostatic stress in the chamber by combining a thin film on a substrate that has a preset bending stress, and then enclosing it in a diamond cell to add additional confining stress. So by using systematic techniques like these, we might be able to choose the amount of shear stress that we have in order to better understand the conditions at which earthquakes occur. Not doing work specifically on the generation of volcanic fluids here, but one of the things that is a really important area for us that's growth in our high pressure field in the future is going to be better understandings of structures of liquids and amorphous solids, and better understandings of melting curves. So I've highlighted here a little bit of our work here. These were the measurements of the liquid structure of the iron nitride from the Paris Edinburgh cell. And these on the right, this is a comparison of the melting curve of carbonates to the experimental conditions at which Ming-Da's experiments took place. So finally, where are we going moving forward? How can we improve to get closer to rock physics and petrology in the diamond anvil cell? So certainly one of the things that we are doing is we need to be developing new techniques. We need to be able to in situ characterize the composition with high spatial precision. The new possibility that we have to be able to do composition mapping with sub-micron precision with our ultra bright APS-U beam is really exciting for us. And if we are able to develop additional techniques, both new cell designs and any other creative ideas that we have to control and measure the stress state in the diamond anvil cell, these give us a new potential to move forward in these areas. I think that we need to facilitate combinations of analytical techniques. I think often that when we struggle as a community to have completely reproducible samples from run to run, it's really important for us to be able to do the same measurements on the same sample. So what we want to do is to come up with ways to better coordinate and cooperate to provide opportunities for multiple in situ analyses on that same sample at the same conditions. I think that more creative ways to solve the problem. We mentioned last night in discussion that HP Sync was originally envisioned to do something like this. So how can we do this in the future to allow us to move around the ring freely? We need to do more work to validate experimental conditions for heterogeneous samples. The more of this experimental petrology that we're seeing, we're still really depending on being able to know something about temperature being homogeneous across that entire experiment where we're assuming equilibrium has been reached. We may also want to come up with more ways to streamline experiments that have many sample changes. When we're doing experimental petrology, we often need to do one cook and then take it off the beam to get ready for ex situ analysis later. So we may be using many more sample changes, many more DACs than a typical equation of state study might use. And I also would argue that we should be continuing to use and develop remote infrastructure because this really allows us more flexibility and allows us to include a more diverse range of new users who have diverse resources. So a few examples here. Now, again, for our multi-technique studies, our studies of iron and other redox sensitive elements, we need to be able to do X-ray diffraction, X-ray emission spectroscopy, Nussbauer spectroscopy on the same sample at the same conditions. Because these spin and redox states can be really complex. Temperature heterogeneity, I noted that we have issues due to axial gradients, due to the medium, the anvil. We have issues due to radial gradients, due to the laser spot itself. But also when we're working on a polymineralic phase assemblage, we are not dealing with a homogeneous medium. There's going to be local gradients. We know that Soré diffusion is an issue. This is inevitable. So we need to continue to be validating our chemistry at these conditions. I think I just got an almost out of time warning. But I did just want to note, of course, that our Beamline staff have done really great things over this year in terms of making remote beam time effective and efficient. They're always really great at making user-friendly manuals and guides, particularly at Jesse Cars, and making improvements in DAC designs that'll help to facilitate the remote techniques. I wanted to remind us to consider the people who are not here. If we're trying to include a broader user community, that may be people who are not in this room. I think that user facility science has a potential to really make science more broadly possible to people with limited home labs. But we know that beam time is competitive. We know that people may choose not to use beam time if we have barriers that keep them from being able to carry out these experiments. In terms of the remote capabilities, I think that going forward into the future, we really think the best team may be one that is a hybrid team, where we have people who are on site. Here's Allison and Mingda, who were on site at our last beam time, our 2 allowed people. We had an undergrad here, Megan, and the rest of us here, we're all remote. This is the best way for us to be able to include more people, support the people who are there local. It's cost effective, it's flexible, and it allows us to include some people who may never otherwise be able to participate in beam time. So thank you very much, and I'm ready for questions.
Thank you, Suki. I love those photos. Do we have any questions here? I had one question. In your slide showing the 2 recovered, or the 2 bridgemanite phases with different amounts of iron in them, how can you be sure that it's not a quench effect, and that, do you see any evidence in the diffraction pattern?
So yes, and I mean, in terms of in the diffraction pattern, we were able to determine that the recovered phase was an Akimotoite. When we compressed it back to the same conditions that the run had been, it was a bridgemanite. We saw the Akimotoite transform to the bridgemanite during the experiment. So we had multiple different runs at different conditions to confirm that this was reproducible.
Great. It looks like, thank you, Suki. It looks like Russ Hemley, did you want to ask?
Yeah, hi. Can you hear me?
Mm-hmm.
Thank you. Great talk, Suki. I guess I had sort of 3 comments. I'm really pleased that you picked up on the language in Earth and Time, and in particular, the definition of critical elements, because that's a very different definition of critical elements than the rest of the government or agencies have. So in that sense, if we are going to have a successful partnership with the DOE, I think we need to speak the same language, because the DOE, in fact, has a very different and more restricted definition. It's just a comment. So thanks for bringing that to our attention. A second comment is on sort of this idea of common samples being examined in different labs. Another way of looking at that is to also make available beam time and funding for people or groups to reproduce other results. Sometimes we sort of go with one shot, gets an answer, and it may be the right answer or not, but it's a big breakthrough. But there isn't often funding to do the follow-up. So I hope that that can be a part of any mission going forward, because reproducibility is really, really important. And sometimes you can't just send samples back and forth. And then the third comment I'd like to make is I'm pleased to see that HB Sync's been mentioned a couple of times. And I helped Dave Mao kick that off at the APS. And it was actually a great idea, and it worked for several years. We applied for funding from Compress early on, but never got any funding from Compress. So that was a missed opportunity. But I think it also just needed continued partnership with Compress and with APS and DOE broadly to be successful. But it's a good idea to bring back.
Thanks.
Looks like we have a question from Renata.
Hi, Suzanne. It was a great talk. I just wanted to, it's a very quick comment. I just want to clarify, I'm sure you are aware of that. That plot that you showed, the book modulus of a Bridgmanite with ferrous and ferric iron as a function of pressure, where of course ferric iron has a high spin, low spin transition. You showed the book modulus at low pressure and at 100 GPa, but across the high spin, low spin state change in ferric iron, the book modulus doesn't vary that linearly. Yes, there is a difference in the middle of the mantle that's quite substantial between the behavior of ferric and ferrous iron. Could you comment on that?
So yes, the plot that I showed, which I can pull up the slide and show again, is from a fixed pressure, actually. It's at 80 GPa, so that I can avoid any worrying about the spin transition.
Well, but it's avoiding the region where they can't make a ferric iron and ferrous iron are really different.
So this is at a fixed pressure of 80 gigapascals.
Right, so, I see. Yeah, fixed pressure of 80 gigapascal.
We are above the spin transition, and this is.
I see.
This was what we found in this condition. But certainly while the spin transition is going on, I know that we have softening that we need to worry about, and so that's why I picked this particular pressure to compare.
I see. So there is no mixed spin state in this plot? Not
in this plot, no. But I plotted an extrapolation of the high spin.
That's extrapolation.
Yes.
But the spin region, that cannot be extrapolated.
Great. If there are no more questions, that concludes this session, and we'll be moving on to an open discussion moderated by Andy Campbell and Tom Duffy.